the Bernstein-Vazirani algorithm, however that's pronounced. So I had initially a bit of trouble understanding this algorithm, but really then I kind of realized it's the same like the Deutsch algorithm. It's using the same principle. So here you've got the definition of the problem. It's basically you've got a function that takes an n-bit string as an input and it just outputs 0 or 1. And so we want to find what's the string that what's the input that gives us just one. It is just one and only one, right? And again, the trick here is that you go through all that and then you realize that at the end of the day, what's happening is that this is formulated mathematically, and then the circuit is kind of defined and inside afterwards. So it might not be obvious. And then one thing that is not obvious with all those algorithms, and it's the same that I mentioned in the Deutsche algorithm video, is that those circuits do not necessarily represent an algorithm. I mean, they actually encode the function mostly in that particular case, and so they encode the function in a way that they give us a solution that we want. That's why you have this one here in the unsila bit. It's the same strategy that's used in the Deutsch algorithm. So basically, that thanks to this, we are creating what I call the negative uncertainty, which means that we're gonna end up in a state after applying all those first gates where we have some of the possible states with a negative phase. And then by applying the control nodes, we're shifting where this phase is. So when we apply the Hadamards again, some of those states cancel out. And that's the concept. So it's basically playing around with positive uncertainty. That's sort of a term that I'm coining, so it's nothing official, and negative uncertainty so that they cancel out each other. And in theory, that I think it's also not needed, the one here. You end up with, if all you're interested in is in measuring those things, that should be enough. And then you can observe here in the explanation, if you want to dive into details, that's exactly what's happening. So you see a bunch of minus signs here, etc., which at the end of the day cancel things out and give you that outcome, right? So if you don't measure the last qubit, you're not gonna see that. So you're gonna just see the 1 1. And basically that's it.